Hello guys, in this video we will learn what do we mean by exploding gradient problem and how this occurs. Okay, so I have listed down some of the reasons here which may result in exploding gradients. So the first and foremost important reason could be improper initialization of the weights. If we initialize the weights to large value, it could lead to exploding gradient problem. Also, learning rate, choice of the learning rate, if it's set to very high, this could also lead to exploding gradient problem. Then if we do not understand the task in hand and by mistake if we choose a wrong cost function or loss function, this will also lead to the exploding gradient problem. Now let us understand what do we mean by exploding gradients problem. Okay, so in order to explain it in a simple terms, I have considered this network where we have only one neuron at each layer and we will consider only one input. Okay, so to update the losses, to update the weights in order to reduce the loss, we need to do back propagation and update all these weights by calculating the gradients at each layer. So in order to update the weight at this particular layer, that is W1, okay, let me subscript it within the superscript it within square brackets. So if I want to calculate derivative of loss with respect to weights at layer 1, with the help of chain rule, we can write it as derivative of loss with respect to output A4, derivative of A4 with respect to its input, which is A3, okay, derivative of A3 with respect to its input, which is A2. Similarly, derivative of A, we multiply these things with derivative of A2 with respect to its input, which is A1, and finally multiply this with derivative of A1 with respect to its input, which is W1, right? So this is what we get with the help of chain rule. Okay, so let us try to understand this particular thing here. Okay, so what is derivative of A4 with respect to A3? Let us understand that. So I'll write derivative of A4 with respect to A3. So we need a formula to calculate this, right? So in order to write the formula, we need to know what is A4 and A3. So these are some activation functions applied on W4 multiplied with A3 plus B4, correct? So this is our A4 and this we can call it as Z4 just to shorten the notation. And similarly, what is our A3? It is some activation function with this particular equation inside, which is W3 multiplied with A2 plus B3, correct? And this we can shorten this and call it as Z3. Now what we will do, we will come to this particular step and again we will expand this with the help of chain rule. Okay, so what we can do, derivative of A4 with respect to its input. What is its input? This is Z4. I am further expanding it. Okay, I am not doing anything else. So with respect to Z4, multiply by derivative of this Z4 with respect to its input, which is A3, correct? So that's what I have written here. Now we know what is this A4. This is nothing but derivative of some function of Z4, correct? This is with respect to Z4 multiplied with derivative of Z4 with respect to derivative of A3. Now, if you check this, let us assume activation function in our case as sigmoid. Okay, and how this looks like? So if I just draw the sigmoid function, this looks something like this. Okay, so this is 0, 0.5, 1. This is our Z, this is our sigmoid of Z. So in this case we are dealing with Z4, let's denote it with Z4, right? We can have any activation functions. I am just taking sigmoid in order to explain it. Okay, so you can consider any other activation functions like ReLU, leaky ReLU, tan-H in order to understand it in a different way. Okay, let's not bother about that. And we know that gradient of this sigmoid will always range from 0 to 2.5. So this is the max what we get. So now since we are using sigmoid function as an activation function, this will be derivative of sigmoid, correct? Derivative of sigmoid. And we know that this ranges between 0 and 0.25, correct? And then we are multiplying with the derivative of Z4 with respect to A3. Let's calculate what it is. So this is derivative of, what is our Z4? Z4 is W4 into A3 plus B4, right? And this is with respect to A3, correct? Now, if you know the derivative, let's take for explanation purpose, let's take 0.25 as our derivative of the sigmoid function. We arrive at this. We will multiply this with the derivative of this particular thing. So if you know how to differentiate, we know that the differentiation of this is W4, correct? Why this is W4? Let's say we have an equation 5x plus 3, right? And we want to differentiate 5x plus 3 with respect to x. So what will be the output? It is 5, right? With respect to x, we have 5, so we get that. And this is just the constant, so this will be turned to 0. So similarly, derivative of this particular term with respect to A3 will be W4, okay? Now, if we initialize the weights to a large number, let's say around 500 or 600, let's say 500, we will multiply 0.25 with 500, right? So what's the value of this? 25 is the 125. So we will get dl by dw4 as 125, correct? Now, in gradient descent, how do we update this W4? W4 is equal to old value of W4 minus alpha, which is learning rate, into dl by dw4. Okay, so this is how we write. So let's consider we have taken learning rate also as 1, which is considered high. Okay, so initially our W4 is 500 minus 1 into what is dl by dw4? This is 125. So what is 500 minus 125? This is 375, correct? So now if you look at the difference between old and new weight, earlier the value was 500, now the new value of W4 is 375. So these two weights are varying largely, right? So they vary with a very large value. So what happens in this case, if you remember how gradient descent works, so let me just draw a cost function. Let me call this as W4 because we are taking W4 in our example for explanation. And let's say this is loss with respect to W4. So if we have a convex shaped curve here, let's say initially the weights are initialized here. So this will be the cost. Since the weights are varying largely, after one gradient descent update, this instead of converging, this may overshoot the minima and come to this particular point. So the new W4 might be here. So similarly, if we go on updating multiple gradients in a deep neural network, the gradients will go on increasing at each layer. So this will be 125. This may further increase from initial value of 500 to maybe 100, or it may increase more than 500 up to 600 or 625 depending upon the gradients, right? So what do we mean by gradient? Again, the differentiation at that particular point with respect to the cost function on that particular weight, right? So it can move in either direction, positive or negative direction, right? So in the exploding gradients will result in divergence of a cost function. So you will see at let's say at one iteration 1, the loss you can see 2.03, and at iteration 2 you can see it getting reduced to 1.02, but in iteration 3 you may again see it at 3.03, and at iteration 4 again it can be 0.1, at iteration 5 it can be 1.9, At iteration 6, it can again go to 4, something like this. So the loss will keep on varying in a large way. So sometimes it looks like it is reducing, but at the next iteration, it will again shoot up. So when you face this kind of situation with your losses at each iteration, you are sure of having exploding gradients problem. Okay. So hope this video is clear. So that's all for this video. In my next video, I will talk about how we can solve vanishing and exploding gradients problem together. Okay. So if you guys are not subscribed to my channel, please do subscribe, and if you like the content, please press like button and share with your peers so that they will also understand these concepts. Okay. So till we see in the next video, guys, happy learning. Bye bye.